Hi all, let's see the next topic of Unit 1, Interrupt Cycle. Coming to the contents, we are going to learn what is an interrupt and how does the computer is going to handle the interrupt with the help of a flowchart. So coming to an interrupt, the difference of information flow between the computer and the input-output devices makes this type of transfer inefficient. Which means that suppose a processor wants to transfer a data to an input output device such as a printer. So in this case, the input output devices in terms of transferring the information, they are very much slow compared to the speed of the processor. So most external devices are slower than the processor. So what happens is whenever a processor wants to perform a write operation into the output register, or whenever it has to take the input from the input register, the processor has to pass and remain idle for some point of time. For example, if you consider a write operation into an output register, the processor has to pass and remain idle until the printer catches up. So at a time it can write only 8 bit of alphanumeric characters into the output register, and it takes certain amount of time. The output device is very slow, so the processor has to wait until the information is transferred from the output register to the output device such as a printer. So the processor has to wait for some amount of time, so it remains idle, so it leads to a wastage of the processor time. So in order to overcome this disadvantage, an alternative method is to let the external device, whether it is an input device or an output device, inform the computer whenever it is ready for the transfer of information. In the meantime, what the computer or a processor can do is it can be busy with some other tasks of executing some other programs. So this type of transfer makes use of a facility called interrupt. So an interrupt is just an interruption of the normal sequence of execution of the processor. The processor keeps executing some other programs. So whenever the input device or the output device is ready for the transfer of information, they intimate to the processor that they are ready for data transfer by means of a special signal called as an interrupt signal. So whenever the processor receives an interrupt signal from the input output devices, it the it processes the particular interrupt routine. It completes the task of the input output. It stops, first of all, it stops the execution of the normal program whatever it is doing till now, and then it goes to the input output devices to handle the interrupt. And once the task of transferring information is done between the input output devices and the processor, then it comes back to where it has left and continue with the execution. So when the input processing is completed, the normal execution resumes. So with the interrupts, the processor can be engaged in executing other instructions while IO operation is in progress. So while the computer is running a program, it does not check the flag bit. So here, in order to let the CPU know that there is an interrupt from the input output devices, there is a flag bit used in the computer. So whenever the computer is running a program, it does not check the flag bit normally. So whenever this flag bit is set, when the external device or an input output device becomes ready to accept or send the data to or from the processor, then the input output module for that external device, it sends an interrupt request signal to the processor, and the processor responds by suspending the current program and branching off to another program that we call it as an interrupt handler program to, in order to deal with the input output devices, in order to send the information or to receive the information from the input output devices, and it then returns to the current program to continue with what it was doing before the interrupt. So So basically, an interrupt is nothing but this is used by the input output devices. Rather than wasting the CPU time, the CPU will be continuing with the execution of the other programs. So whenever these input output devices are ready for transferring the information, they intimate the CPU with this type of a special signal called interrupt request signal. So whenever the CPU receives an interrupt request signal, it stops the currently doing activity and it will handle the input output device request interrupt request signal. And once it was done with the interrupt handling, then it comes back to wherever it has stopped the previous execution of the program and continue with the remaining instructions of the program, executing the remaining instructions of the program. This is how an interrupt is handled by the computer. So the interrupt enable flip-flop can be set and cleared with two instructions, I off and I on. So in case of input output instructions, when we discussed about input output instructions, I have already told you there is a flip-flop called as an interrupt enable flip-flop. So whenever the processor want to receive an interrupt from an input output devices, then it can set to 1. Whenever the IEN is set to 1, then the processor is ready to receive an interrupt from the peripheral input output devices. And whenever it is set to 0, it means that the CPU at this point of time it doesn't want to receive any interrupt. So when an input device or an output device want to interrupt the CPU, it can only interrupt the CPU only when the IEN is set to 1. If it is set to 0, no input device or an output device can interrupt the CPU. So the flow chart, so this is a flow chart of how an interrupt will be handled by the CPU. So as we know, uh, the execution of an instruction in the case of if you see a program, it is nothing but a set of instructions where each instruction of a program has to go through a cycle called instruction cycle. So we have already discussed about instruction cycle where we come across different steps of the instruction cycle. Each and every instruction has to go through these steps which are present in the instruction cycle. The steps are nothing but first step is fetching the instruction, second is decoding the particular instruction, and third one is execution of the instruction, and finally write the results, right? So fetch, decode, and execute. These three steps are very important for each and every instruction that is present in the program. So if you see a flip-flop here, in order to handle the interrupts, we have a flip-flop present in the hardware of a computer called R flip-flop. So whenever this R flip-flop is set to 1, it means that there is an interrupt from the input-output devices. Normally, the execution of the instruction of a program starts with the instruction cycle, and the CPU fetches and decodes the instructions. And after fetching and decoding, it will continue with the execution of the particular instruction. Meanwhile, when this particular instruction is being executed by the CPU, the control of the particular computer, it keeps checking the flag bits of input output devices. So it it will first check interrupt enable. If the interrupt enable is 0, then no input or an output device can send an interrupt signal. So it will continue with the next instruction. So if the interrupt enable is set to 1, then there is a possibility that there might be an interrupt from input device or from the output device. So when IEN is equal to 1, it first checks the FGI flag. If the FGI flag is set to 1, it means that there is an interrupt from the input device. If the FGO flag is set to 1, it means that if FGA flag is set to 0, which means there is no interrupt, then it keeps checking the FGO, the output device flag. So if this is 1, in both the cases, if any of the flags is set to 1, then it will set the interrupt flip-flop R to 1, which means it is setting the flip-flop to 1 so that the CPU will now come to know that there is an interrupt from input output devices. It can be from the input device or from the output device, but there is an interrupt from input output devices. So once the execution of the instruction of a particular instruction is done, then the CPU goes back and it checks the value of R flip flop. So when this is set, the R flip flop will be set to 1. Now when it checks the R flip flop, if both the FGI and FGOs are 0, then R flip flop, the value of R is 0. So it will continue with execution of the next instruction according to the program order. Otherwise, if R flip flop is 1, if there is an interrupt from any one of the input output devices, R will be set to 1. In that case, the CPU will move on to the interrupt cycle. So in order to handle that particular input output device request. So in that case, before handling that particular interrupt service routine, what the CPU has to do is it has to store the currently executed whatever task, whatever program that is being currently executed by the CPU, it has to store that particular return address. So wherever it has stopped, that particular address has to be stored in some location of the memory. And then it should move on with the interrupt service routine. So whenever in the interrupt cycle, what it will do, it will store the return address. Return address is nothing but the address where the particular CPU has stopped executing in the currently executing program. So that particular address will be stored at location 0 of the memory. Usually we can store it either in a stack, this particular address, or a register, or any memory location. Here it is storing it in a memory location at a location 0, the first location of the memory. So the PC value, so when say for example I have 10 instructions in my program and I am currently executing, the CPU is currently executed the 5th instruction. So then the PC now points to the instruction number 6, right? So the address, the whatever that PC stores the address of the next instruction, which is instruction 6. That particular instruction address, whatever value is in PC, that will be transferred into the memory location 0. And then it will branch to the location 1. So the PC will now be incremented by 1. So now PC points to location 1. So at location 1, we have the interrupt service routine program. So at the same time, the interrupt enable, since it is handling the interrupt enable will be set to 0 and R flip flop will be set to 0. So once this particular thing is over, interrupt service routine, then it will continue, it will go back and start wherever it has left, whatever memory location, it will go back to M of 0 location where it finds the old value of PC and it starts executing. So let us see this interrupt cycle with a small example. So here if you see an interrupt flip flop R is included in the computer. When R is 0, the computer goes through an instruction cycle. It continues with the normal execution. During the execute phase of the instruction cycle, the control checks the IEN, interrupt enable flip flop. If it is 0, it indicates that the CPU or the programmer does not want to use the interrupt, so it continues with the next instruction cycle. If interrupt enable flip flop is 1, then the control checks the flag bits. If both the flag bits FGI and FGO are 0, it indicates that neither the input register or the output register are not ready for transferring the information. So in this case, the control continues with the next instruction in the instruction cycle. For example, if the either of the flag is set to 1, whether IE an input flag or an output flag, in that case, the flip-flop R will be set to 1. The same flowchart is explained here. So at the end of the execution phase of the current instruction, the control checks the value of R. And if it is equal to 1, if the R is set to 1, it goes to an interrupt cycle instead of instruction cycle. Rather than executing the next instruction, it handles the interrupt by going to an interrupt cycle. So this interrupt cycle can be explained with the help of branch and save address operation. So if you see the memory here, before an interrupt has occurred, so currently this is your main program where the CPU is currently executing. And consider CPU is executing an instruction 255 of the main program. And whenever this 255 is being executed by the CPU, program counter points to the next instruction, address of the next instruction, which is 256. Right? So, so this is my main program. This is my input output routine program that that has to be executed when there is an interrupt. So here this is the before interrupt. So whenever an interrupt has occurred, so say an input or an output device has sent an interrupt request to the CPU through a flip flop. So when in that case our flip flop will be set to 1. So in that case how the CPU handles the particular interrupt. So in that case what the CPU will do is at a location 0 of the memory it saves the value of the PC which is 256. And the program counter now points to the next location. It will be incremented by 1. So the PC value will be now 1. At one location, we have an branch, unconditional branch instruction. So in case where the I bit is 0. So which means that if you go to that particular address 1120, you can find the interrupt service routine program, IO program, where the particular service will be provided for the input output devices for the by the CPU. And once this interrupt service routine has been completed, at the end the last instruction of IO program will be unconditional branch instruction. So with an mode bit 1. So if the mode bit 1 it means it is a indirect address. So the address is 0. So if you go to this particular address you will find the address of the particular PC value in this particular address. So 256 0, if you go to 0, 256 is nothing but the value of PC which is the next instruction that has to be executed. So what the CPU is doing before going to the interrupt service routine, it is storing the PC value into a 0th location of the memory, and through this branch unconditional instruction it is going to the interrupt service routine program. And once this particular interrupt service routine has been completed, the last instruction is again a branch unconditional instruction with a mode bit 1. So if you go to this particular location 0, you will find the value of PC. This is not the direct program. This is a, if you go to this particular address of the memory, you will find the actual address. So 256 is the actual address. Now the PC value will now again becomes 256, so that the CPU will start continuing with the main program, the next instruction of the main program. So this is how an interrupt will be handled by the CPU or the computer. So let's see this in the form of micro operations. So the interrupt cycle is initiated after the last execute phase if the interrupt flip-flop is equal to 1. When this flip-flop will be set to 1, it will be set to 1 if interrupt enable is 1 and either FGI or FGO flags are equal to 1. And these things can happen only with any clock cycle except at T0, T1 and T2. Because at T0, T1 and T2, if you see the flow chart, the fetch, decode and instructions takes place. So as we have already seen, we are going to fetch the instruction at clock cycle T0, decode the instruction and fetch the source operands and at clock cycle T2. So, so T0, T1, other than T0, T1, T2, this particular flip-flop will be set to 1. So, during the execution phase, which means at T3, this can happen with any clock transition except when the timing signals are T0, T1 and T2 are active. So, the condition for setting the flip-flop is 1 can be expressed as So T naught dash, T1 dash, T2 dash, which means other than T naught, T1, T2 dash means. So when IEN, FGI, FGO are enabled, then R flip-flop will be set to 1. If IEN is 1, at the same time FGI or FGO or both. If both are ones or either of them is 1, then R flip-flop will be set to 1. So, what happens when the R flip-flop is 1? It goes to the interrupt cycle. So, the interrupt cycle is represented by R. So, at a timing in the interrupt cycle, what happens? The address register, the contents of the address register will be first pointed to 0th location. So at the 0th location, we need to what you say during the first timing signal, the AR is clear to 0 because at the 0th location of the memory, we have to place the value of PC, right? Whatever is pointed by PC. So and the contents of the PC is first transferred into the temporary register at a clock cycle T0. At a timing signal T1, the return address, whatever is there in the temporary register, the old PC value, it is transferred into the particular memory location pointed by the address register, which is 0. So at M of 0, at the address location M of 0, the PC value which is transferred to the temporary register is placed into the 0th location of the memory. And PC will now be clear to 0. At the timing signal T2, the PC will be incremented by 1. So that PC will now becomes 1. And interrupt enable will be set to 0 and R flip-flop and sequence counter will be cleared to 0. So that is what happens uh, in case of interrupt cycle. Okay. So the interrupt service routine will be executed, and as per the diagram, after this interrupt service has been completed, it goes to the 0th location of the memory and it points to the old value of it. It contains the address of the next instruction that needs to be executed by the CPU. So this is called interrupt cycle. This is how the interrupts will be handled by the CPU. Thank you.